Patchscopes. And it is my pleasure today to introduce Shivam Raval. Shivam is a grad student in Harvard Physics, and he works on a broad range of topics having to do with machine learning, use of machine learning for real problems, interpretability, and visualization. Shivam has been collaborating with us in a couple of projects involving visualization of representations of X-ray data, and more lately involved in trying to work some multimodal aspects of LLM. So I'm very happy that this is gonna be the first speaker of this semester, and please tell us about whether language models can explain themselves or not. Floor is yours. Thank you.
Thank you. Thank you, Rafael.
Oh, please, sorry. This is supposed to be a very interactive thing, so feel free to interact with questions anytime, all right?
Yeah, so hello everyone, I'm Shivam. As Rafael said, I work on a broad range of things, but right now I want to talk about machine learning interpretability, mostly for LLMs. But if, let's say you're not working on LLMs, there are some insights that might be things that could be applied to whatever models you're working on. So depending on where you are in your research and what you're doing, maybe this applies to you broadly, maybe this applies to you specifically, maybe the techniques that we are talking about are some things that might be useful for you in your work, maybe not. You just maybe get to know how ChatGPT works. So just take it as you see, and if you have any questions or if you have any thoughts, comments, let me know, but I will have like 2 or 3 checkpoints in between where I will stop and wait for more questions. But if you have something that's a small comment, or if you see that something's wrong on there, please let me know. This is something I made in a very rushed effort, but thank you. So what I'm going to talk about is something that people have been debating lately. Can we use language models themselves to figure out what they're doing? Or are we the ones who have to sit down and figure out what language models are doing? Let's see if this works. It does not.
Need to click on the. Yeah, not sure.
Okay, so this is work with a whole bunch of people. My advisors, a postdoc in my group, Andrew Lee, Martin Mortenberg, Fernando Viegas, some professors, Melanie Weber here, postdoc, some people at Google, and Neil Nanda, who a lot of people know. Let me start with just a random conversation I had with Gemma once. This is Gemma because it's an open source model. You can reproduce this conversation. You will get this exact answer, but you could do it with ChatGPT. You can ask, well, I asked Gemma one day, who is the Einstein of chemistry? If I think about it, like, it doesn't really make sense. Like, what does it mean to say if someone is an Einstein of chemistry? It could also be that the language model might think that I have made a spelling mistake and I'm asking for Einstein and chemistry, but no. What it responded with is, it thinks the answer is John Dalton. Firstly, it thinks, so I don't know how true that is, but whatever it does, whatever it did inside, it came up with John Dalton, and it gave a reasoning as to why it thinks that the answer is John Dalton. And it makes sense. He was the first to propose the atomic theory of matter. It could be any other chemist, but it was like one of the pioneers. But we could play this game over and over. Then I asked, who's the Einstein of organic chemistry? Yeah. He came up with Robert Burns Woodward, who came up with the selection rules for spectrochemistry. Also makes sense. Who is the Einstein of radio astronomy? He came up, well, Gemma came up with Jansky, who first detected the radio tones, the radio waves. Sorry. I can keep going. Who's the Einstein of impressionist art? Gemma says it's Monet. Then I say, who's the Einstein of F1 racing? Now Gemma is annoyed, but it still gave me an answer. I don't know if you all agree with Gemma, but she thinks Lewis Hamilton is the one. He's the Einstein. But this begs this question, like, what is the model actually doing? Because it's not giving me an error, it's not saying that I'm incorrect, but it's accurately figuring out that being an Einstein of something is not like the Einstein person, but it's like being the best or the pioneer at something. So if I naively think about it, it's sort of like doing some weird computation that has Einstein as one variable, physics as another variable, and all of these other fields as another variable, and somehow producing an output that makes sense. But if I, again, like naively think about this, does it mean that like Einstein minus physics plus art equals Monet? Well, not technically, but there are people who are working on something like this, and maybe this is kind of how all the diffusion models like models work, where they compose multiple things together, but we don't know. We go back to this simple thing. Let's say we don't know what a function is, we would linearize it. So the first approximation is this, what is happening inside this complicated model when it's trying to do like this composition of Einstein mixing with something else, but removing the concept of physics. We don't really know, but this is a growing hypothesis that people have, that even though these models are complicated, they are trained on a whole bunch of data, but somehow they have some sort of a linear representation of the world in them. What I mean by this will be clear a little bit later. This is something that people found in older models, not Gemma, not ChatGPT, not Llama, not any of the newer models, but previous ways of encoding text had these vector computations that sort of made sense, and you could reproduce these. So this was a very popular example, king minus man plus woman. The vectors for all the words would give the vector for queen. So there was a sense of direction going from woman to man, which was parallel to going from king to queen, and the same direction when added to each and every one of the base words would give you the royalty words. And the same, like man plus royalty was king, and woman plus royalty was queen. Similarly, what people found was that there was, again, a relationship between the capitals and countries, and it was almost linear. So capitals plus some vector direction would give you the country, or country plus some vector direction would give you the capital. Now, the question is, does this sort of work for LLMs? And kind of yes. If you actually go into these open models, figure out what the internal representation at a particular layer is for, let's say, a phrase which has a male pronoun, a phrase that has a female pronoun, subtract the vectors physically, approximately, they would give you the same difference as the difference between like king and queen, between king and queen in French, other things. So there are these like sort of linear representations of things inside the models. But now the question is, can we use these linear representations to figure out what the models are doing? The answer is sort of yes, but we need to know what the models are doing a priori, and we need to know what we are looking for. I'll show you an example. This is a whole bunch of data that I generated from the internal activations of Gemma 2 to be at layer 22, and I have embedded a whole bunch of like male sounding nouns, a whole bunch of female sounding nouns, pronouns, words in general, and I'm doing a PCA on the first two dimensions. And as you can see, there's like a very clear line. If I had way more data points, it would be even more clearer, but at least even in this, you can see that I can naively draw a line, and everything above to a certain extent is male, everything below this line is more or less female. Similarly, again, I could generate a whole bunch of names of countries, some capitals, and I can like project them in 2D and draw a line, and that clearly separates it. Now, the caveat here is that, yes. Oops. Sorry.
So these RPCA projections of embeddings generated by LLM?
Yes. Yes. So one caveat here is that if you think about the variance explained, it's low, but you still see some linear structure. So I don't believe that like all the features that you see in the LLMs are like very linear, but what I can say is that somewhere deep within, there is some sort of a manifold that's almost linear, and things which are like going above and below, so that you can approximate them to be linear-ish, which is kind of what my hypothesis was in the beginning. Let's say if the model is doing something very complicated, you can sort of linearize it. Some features are easily captured in that linear version, some features are not. Now, as I said before, you need to know what you're looking for, and that's what is generally called probing. What you do is generate a whole bunch of data, label it, or generate some labeled data, observe how the data is represented, either like you do PCA, t-SNE, or you fit a logistic regression model to find the best separating hyperplane, which is sort of what people generally call as the feature direction. So a simple example here, if I have some data points that correspond to a dog, some to a cat, I can draw a line, and this is again like a 2D representation, but the logistic regression is usually fit on the higher dimensional data, so it's not in 2D, but the 2D is just for visualization. But this is how, if you have data, if you know what directions are, then you can generate these contrastive pairs, like positive, negative sentiments would give you the direction for what the sentiment direction is. English and French would give you the direction for going from English to French. Now, the bigger question is, why even represent features linearly? I do not know. This is ongoing research that people have been thinking about. I am not. One hypothesis is that features are linear to an approximation, but not really. This paper that just came out puts another hypothesis where if there are certain conditions in the data that are satisfied, then the emergence of linearity is more likely than other cases. Another hypothesis that a lot of people have is that this is an artifact of quantization during training. Maybe like in a perfect world where we could infinitely and precisely represent all concepts, things would be very nice, but because we truncate the data while training, that leads to some artifacts and things are not as perfect anymore. But again, like none of these are things that I have thought deeply about or verified. I think this is the same example as above. Now, the other thing was that this is a projection of some random layer I chose. Things are not that clear if I choose some other layer. This was a cherry-picked example. This is a non-cherry-picked example. Colored by the same things, you might see that the best separating hyperplane between two obvious clusters is not something that aligns with male or female or just country and capital. There's also something else. So in this case, this is the line that separates the countries and the capitals, but there's also this line that separates these clusters versus these clusters. So you can make your own hypothesis. I've listed some words from each and every cluster, but if I just look at it, maybe that I can come up with some explanation. I don't know a priori what the reasoning behind these clusterings is. Like country and capital makes sense, but why group like Australia, Chile, Barbados, Cameroon, and like El Salvador, Bhutan, Kyrgyzstan separately? I don't know, but the language model does know. So the other thing to think about here is that the variance explained here is like very high compared to the previous example, which means that like if I go to maybe 3 or 4 dimensions, I could explain most of the data very, very well. So maybe inherent structure at this particular layer inside the model was maybe 3 or 4 dimensional. And this feature that is separating them is an important one that the model figured out at this point. Again, this is all speculative, but this is one way where people try to empirically do interpretability studies. Okay, so now the bigger question is, why does this all matter? Like, why do you even care about looking into the model that deeply, or like all of the empirical studies that even find like one neuron or one feature that corresponds to sentiment, toxicity, all of these random things? I have distilled them down to 3 things. There could be any more, but the first and most important one for a lot of people doing AI safety is transparency. You need to know what the model is doing, where the model has figured out certain things, what kind of circuits are inside the model when it's performing a task, etc. Now, if you understand it, then you can control it. That is also something that is important. Let's say you want your model to not be giving out private information. You need to be able to control it such that you are sure enough that it won't do that. And the next and the last thing is safety. You also want the model to be unbiased, non-toxic, should not be, or should be well aligned to human values, etc. Okay, so I have another example. Just have a look at all of these cities and which countries they are in. Maybe some of them are right, maybe some of them are wrong, maybe all of them are right, maybe all of them are wrong. Do you have any sense of which ones are correct, which ones are not? I'll give you like 1 minute. Can anyone come up with one example of this which is right or wrong without looking online, or like looking at Google?
Well, Lotz sounds like a weird name for a Dominican Republic. city,
Okay,
But maybe, I don't know.
Riga is in Latvia. And Riga is really in Latvia. And
Yeah.
and Ульяновsk is probably in Ukraine.
okay.
Cote d'Ivoire is correct.
SB is not in China, right?
We shall see. So I have generated,
She said because you had 2 China, so one of them must be wrong.
no, I have like 1,500 examples like this.
Oh.
This was like a small subset. If you wanted to look at all 1,500, you could, but I'll give you an easier way to do it. You just project it using some internal layer of a language model. They automatically cluster, and the language model, if it's trained well, knows which are correct, which are not. So there is a direction of factual correctness inside the model. And well, this is the answer. So people like it because somehow they can say that the language models know what's true, what's not. That is not entirely correct. The models don't have a sense of truth. They only know what the training data is reflective of, and if they have seen some facts a lot of times, that's something that they sort of clustered them together and think that they're factually correct. But you can use them as ways to either look at some data and see what level of factuality or hallucination the outputs have. Yes.
Is there a reason why the factually incorrect representation spreads over a larger portion of these representation space?
Yes, because there is a higher probability of seeing factually correct data. And I feel like I would assume that the language model clusters them closer together based on like how much more it has seen. But there's a higher variance of factually incorrect data because like there's only one way to say the right thing, but like 20 ways to say the wrong things.
Really is not intellectual.
Yeah,
Okay, then it's the language model's problem. Okay, so what else can you do with this? So this is some of the recent work that my lab just produced and I was a part of. If you know what features you're looking for and you have trained probes on these features, what you can do is allow users to control for it. So what we did was to come up with sort of a dashboard that lets you change the LLM's model of you. This is not the LLM, but what LLM thinks you are as a user. So if you're talking to an LLM and say that, well, you have a lot of studies to do, it probably assumes that you are a student. If you say that you like to wear a dress, it would be more likely to believe that you are female. These are correlations and associations that it has learned through training. It doesn't believe that there's only male or female genders. It doesn't believe that. But if you just look at the probabilities, it's more likely that it will think that you are a female, and its outputs would reflect that. So you can try this in any language which is gendered. If you start a conversation in Spanish, Portuguese, if you don't mention your gender, but use any gendered pronouns or nouns, then its outputs would reflect that and its model of you would change. But you can also tweak that, because if you know which linear direction corresponds to gender, all you need to do is go from the female gender cluster to the male gender cluster, and the model would believe that you are male, even though you started the conversation with female. So we just externalized this and allowed users to play around with these parameters and see what kind of outputs the model generates. And sometimes it was useful for the users to actually correct the model's mistakes. Maybe the model thought, well, like, I like Linkin Park. Maybe it thinks I'm like a teenage girl, but I'm not. I just like Linkin Park. And I would want the model to correct that, because if I'm asking for some other suggestions later on, I don't want it to make its case based on thinking that I am a like 16-year-old girl. So I would want to correct for those errors in the model's perception. And this is just one way to allow control. The last is alignment and safety. You can find vectors that are sort of cleaning away the toxicity and would let you generate non-toxic outputs. But again, all of this relies on the fact that you are able to figure out what the features are. If you know what you're looking for, then you can come up with some examples and find these features as directions inside the model. All right, any small questions, any thoughts, comments? Yes.
So maybe you're gonna talk about that.
Why if it's so clear, what are the right answers and wrong, if there's a clear catch, why would it not hallucinate? Why would it give you the wrong answers? Isn't it easy to just adjust like you did for gender for correctness? Yes.
It is, but the model is statistical. So even if it knows the right answer, there is a chance that it might produce a wrong answer, because all that happens in the next generation is it's choosing a token based on some probability distribution. If you run that probability distribution output like 10,000 times, it would generate the wrong answers a couple of times. But let's say it started with the wrong answer, it's like a chain. It will keep going because it needs to sentence complete such that a human is understanding the outputs more than whether it's correct or not, because that's how the models are trained. After sentence complete, they're trained to sound more nice to humans. Yes.
You mentioned a lot about the linear hypothesis. So I'm also curious if people also try to study like non-linearity, like
Yes.
deviation from the linear relationship.
Yes, so actually my advisor had a paper where they studied this in a small setting of Othello. It's a simple enough game that you can train a transformer on it, and you might see nonlinear representations arise because of looking at certain features, but if you instead look at different features, you might find them to be linear. So it's not completely clear right now whether like there are nonlinear features or what nonlinearity even means here. But I think more research is required in this field. Yes.
In your previous. Where you covered how the model breaks down on the probability of gender, age, blah, blah. Are those categories things that naturally came out of the PCA, or are those labels that you imposed because those are obvious? And is there any other category that is?
It's doing this over a lot of categories. Like we had categories for race, we had categories for socioeconomic status, for gender, race, country of origin. All of these are things that are very easy to figure out.
Yeah.
We just kept all the ones that you see because this was something that a user was going to see, and we didn't want anything that might be too sensitive for them.
There's also a question online. Natasha, I don't know if you want to unmute yourself and ask, or I can ask.
Yeah, sorry, I'm her son and I do AI data science stuff. I was wondering if there are certain algorithms that are preferred for like clustering when you're looking at factuality, and if there's like noted differences in performance in terms of the output based on what clustering algorithms you use.
I think so. So there's a lot of work on truthfulness and factuality. There's a method that came out. It's called contrastive, consistent contrastive, something CCS. But this was by Colin Burns, who's now at OpenAI. What people found after his paper was that there wasn't just one direction of factuality, but there were like many. You could train a direction such that it was constrained to be orthogonal to the one that was found in that paper, and you can find like 20 such more directions. So I don't know whether there's a method that's better or worse, or there's just one direction, but you can also try that. Yeah, if you train one probe to find a direction that classifies factual, non-factual, you can also constrain another probe to be perpendicular to the first one and keep going and play this game and see how many you can find. I think you can find many more than one. Yes.
In the case where you have these sort of unintuitive separations, these clusters of king queen on one side and these nephew on the other, are those reproducible either between LLMs or within the same LLM for a slightly different training mode? In other words, is there a signal there that it's seeing, or is it kind of random?
Yeah, I think that's reproducible. I can give you the code and you can also get the same figures.
I mean, reproducible between LLMs, will they all find these different?
No, I have not looked at that, but that is a good question. I will look into that. Yes.
Your plots and at the bottom of your slides, you mentioned projections of specific layers. And those points have me wondering how knowledge is spread across layers.
Yes.
Large language model, have people explored that and whether different divisions are possible, or whether like further up in the network, further versus deeper down?
You will see something later on. Okay, so probing was just one way to interpret what the model's doing. Another is something that just came out of Google lately. You just let the language model verbalize its mental communication and see if it actually is able to communicate what the internal model is like. And you can also investigate many other hypotheses than just contrastive pairs of sentiment, etc. I will give you an example, but the method that they came up with is called Patchscopes. It's nice name with scope in the end, which is like the current trend right now. There's Gemascope, there's Patchscope. Well, you would be disappointed or not, but what we build is called Lumiscope. But the method Patchscopes is very simple. All you do is run the model once. And I remove this.
You can just take it out, right?
Yeah. More.
More.
And then hide floating view controls.
So what you do is pick a source prompt, run the model once. Go inside the model, pick up an internal activation for a token at a particular layer. And then you construct another prompt that's sort of encouraging the model to output something that's sort of the information that you're looking for. So in this case, I want to see which layer inside the model has figured out that London is in United Kingdom and it's the capital and it's the largest city or whatever. And if you play this game and inject this prompt at different places inside X, at some point the model will stop outputting X, but will start outputting London. And the place where that happens is where the model sort of has figured out this association. That's the basic method of Patchscopes. You can also think of this as generalization of like other approaches. There's something that is called logic lens. Basically, what you're doing is trying to see how the model's outputs change as the information progresses throughout the layer. It's kind of the same as saying, I will patch all information from each and every layer to the one that's right before the output. That's kind of saying the next computation at each and every layer will be whatever gives me the output. And so this is equivalent to a logic lens. Okay, so more formally, you feed the source prompt into the model, collect the hidden state representation, feed it to a target model, and patch in the activation from the source and look at the outputs. Now, the benefit here is that you don't need to do any training. You can sort of figure out your task and construct a prompt such that you can extract that information from the model, and you don't need to have these contrastive pairs or train any probe or anything like that. And the choice of the task is up to you. So that is all nice and good, but now we had another question. I am a visualization researcher. I do Wiz, a little bit of AI, but I look at this and this is not how the method is actually implemented in practice, because you have to write a whole bunch of code, you have to implement a bunch of hooks that are model specific, figure out where that token information is, that token ID that you're looking for, extract that, have another hook at some point inside the model that runs while you're running the inspection prompt, and it figures out the right token index where it needs to patch in information, and then patch it, and then output it. What I thought we could do was, well, not do that, but just have a simple interaction that lets you do all of this complicated patching. And I will give you an example with a demo that hopefully works. The demo starts now. All right, this is an older model because I wanted to run fast. It's Pythia, if anyone's interested, and I think it's a medium-sized Pythia, but I'll just explain how the method works in practice. Let's say I want to figure out at which place this exact relation of country and capital is figured out. I will just take my target prompt to be some few-shot version of country, capital, country, capital. Does anyone have a favorite country?
Colombia.
Okay. And I made a spelling mistake. All right, let's see. So now I want to patch in maybe, I don't know, I have a hypothesis. It's an early layer information that could be, well, I also made a mistake in the target prompt. Should be X, because I don't want to patch it to United Kingdom. I want to patch where there is no information. So let's just do this. That's all it takes. I've patched it. I just need to run my function and it'll generate an output. So source prompt to target prompt at X. outputs Tokyo, which is wrong. So that is not correct. Let's just do all possible combinations and see if the model has figured it out somewhere inside. I'm not sure though, because this is an older model, it's simpler, who knows, maybe.
Do you know what the capital of Colombia is?
Yes, it's Bogota.
Yeah, that would be a good test.
But it's an interesting test because Columbia is a university, it's a district, it's many things.
Yes.
Well, the country is spelled with an O instead of an U.
Ah,
Yes.
very good, okay.
Okay, so this will take like a minute to run, but in the meantime, I will go back to my presentation and see if there's something that I can show in the meantime.
So could you actually explain a little bit what's happening in that notebook there? Just so you've done a prompt.
Yes.
Can you explain the whole patching process a little bit better?
Okay, so the whole patching process is, I run the model once with the prompt Columbia. I collect all the internal activations of all the tokens when the model is run once. That all information is present here, and all you have to do is like do this interaction of here to here. The target prompt is what will be run once my interaction is complete, because in the second run, what I need to do is take this information of the representation of Columbia and patch it somewhere inside for X, but I don't know where exactly. So I need to do that either at the first layer, second layer, any layer, all layers. At some point, the model maybe figures out that it's supposed to say something that makes sense. Let's look at the outputs because it has given me that.
So. Nine Tara had a question.
Yes.
I am tired one.
Yeah, sure. My question was just if you're using the Patchscopes method to score how likely it is that a certain capital is indeed the capital of a certain country, or like in whatever context, like how does it correlate with using log probabilities to score a certain answer for models that allow you to generate log
Yeah,
probabilities?
I think that is more principled because in this case, the output would be the one that has the highest log probs, but I can imagine that in scenarios where like just one patching operation is not enough, but is enough to push the log probs of the right answer up. What we would want to do is look at the diff between the log probs between no patching for all layers, and I think that is something that's totally doable. I don't have it right now, but that's something that we plan to do. Because that's more principled, like it might be that the model has in that information and that association, but it's not strong enough that it can output it. So Colombia is not strong enough, but maybe France is.
I think probably Argentina is strong.
Let me run France once.
So how relevant is it that France is one token, but Colombia is three?
Yeah, that is also something that affects a lot of models' outputs. The newer models don't have this issue because they are they have like a context size of like 150K or something, but this was a smaller one, so hopefully, I think. Oh, not here. Argentina, France.
Argentina won the World Cup.
That's what's important.
All right, no guarantees that will win here, but sure. Okay, like it will take some time. So what can you do with this method? Yes.
Sorry, I don't think I quite understand what the different columns are doing.
Which columns?
Sorry, I don't quite understand what the different eyes are doing in this whole visualization.
Okay, so this is a visualization of like the transformer layer computation. This is Pythia, which has 24 layers. So each and every eye is a layer index. And so one operation of like me bringing an arrow from top to bottom is just in its forward pass of the target prompt, taking the information at this particular layer in the forward pass of the target prompt, patching it at this layer as if this was the information at the output, and then letting the model continue its run and generating the output. And that is operationalized like n cross n times right now. So one operation is just taking information from a certain place in the prompt. In the other prompt, patching that information at a certain point and letting the model just run as it were. But the problem right now is that we don't know which one is the right place to patch in, because that's something that you need to like have an intuition of if you have built the method or play around with or figure out, at least for the task that you're concerned with, whether it's doing the right thing or not. Let's see, this is almost done. Nope. This is not a good model, so well, let me just look at the answer first.
There is Buenos. Yeah, Buenos Aires is there.
Where do you see Buenos?
Oh, yeah, I think Buenos Aires is there.
Yeah,
You left-
Oh, Buenos is there.
yeah, you left Google in your hands.
Ah, yeah. Okay, yeah, this is where the model figured out.
How many questions?
So what does this mean? Figure out from the very first layer or?
More or less. So that information is early on. So this is something that people have found, that in the early layers, the entity decoding stuff happens, like what is Colombia, what is Argentina, and stuff that's related to it. Deeper inside is something that people call entity resolution happens. So if there's something that like Colombia could be many different things, which is not the case, but if there were such things, then to figure out what is the right context happens deeper within. And towards the end, it's more on the generation. So you would never find like the right stuff towards the end. It will always be X or something like that, because all it needs to do is look at the previous and generate the next. But deeper within is where like interesting stuff happens. And you could do many other things, like let's try this. This is a complicated example because I've chosen like not so popular Harry Potter houses. I don't know if people have Harry Potter trivia, but these aren't like Luna Lovegood was in Ravenclaw. I did not know that before I searched this.
How we can make model working better, like what else it can be done to improve it? Because I think the Argentina case is about 10%, 10 to 15% correct.
Mhm.
Count those so how you can increase that?
So a few things you can do is they're fine tuning, like if the model is not performing on that specific data, then you might want to nudge the model a little so that it knows that data better, because all this is like how much the model has learned the associations. And if it hasn't looked a whole bunch of that particular subset of data, it wouldn't have learned those associations. So maybe it only saw like Bogota a few times, but it saw Buenos Aires more, so maybe it remembers it better. I think Gemma is better at this.
It's a flawed model.
Yes. It's a very flawed model. It's a.
So does that mean that you need to increase your training set?
So you might want to fine tune, it might not be the training set, because it depends on your end use case. Because let's say if you are doing a lot of actual Astro work with the LLM, and it's not really that fine tuned or that pre-trained on Astro data, then you might see that its outputs are not that reflective of what you wanted to do. And maybe that's something like, okay, that is a very mechanistic case. You might not want to drill down inside the model to go that deep. But if you were interested in doing that, and you might find that like these information associations are very sparsely located, like if you want to know something about like different types of astronomical objects and other things inside the model, and you find lesser associations of that, maybe fine tuning would make that better and make the model better. But this is also a way where you can test bias inside the model. So we've tried this example instead of like having a person and like some entity or something like that, we had an example where you have someone's name and a profession, and we had a mix of like male dominated professions, female dominated professions, male gendered names, female gendered names, all balanced. But the model, if it was patched in with a female gendered name, would always output like feminine characteristics more than professions. And for the male, it would output mostly like professions which are male dominated. So for example, if I have like, well, let me also show you that example, but in the meantime, let me run this.
And there is a question from online again, Mike.
Yes.
Do you wanna ask?
Yeah, I was just as a follow-up to what you were just saying, I was wondering if you've tested the visualization before and after a fine-tuned model to see if your fine-tuning was actually effective in you know, adjusting the knowledge of a certain topic.
No, but that is a good question because I just made this last week.
Okay.
But this could be one of the use cases. So we are excited to try out a whole bunch of things because this allows you to like not worry about the implementation, but just focus on like what examples are interesting. Yes.
Following up on what Doug said, like in this case, I see you're choosing a different token than the last one. So like, is this just a feature of the visualization, or are you taking the whole prompt or just one token at a time?
No, I'm taking the Potter prompt. I just realized that like is in doesn't really
Okay.
make that much sense. I could do that. I could also pick in, but for now, I mean, Potter is where the most information should be located. So I chose that. I could have chosen the last one, like in. So that's also totally fine. It's not a bug, it's a feature. All right, let's see.
Sorry, I have a quick
Yes.
question. Does this kind of visualization also helps with like determining which part of the prompt, like the LLM is focusing on when it's trying to like output something? Like
We haven't thought about saliency in this visualization, but that is something we can think about. Because yeah, I think that is also an interesting question. All right, so it doesn't really care about Gryffindor. And just to be clear, it would not output the whole Gryffindor, it would just output GDIF, right? This, because like Gryffindor is not in its vocab. But only here. That's it. But it does know that Harry was in Gryffindor. So it could also mean that if I like mess around with these layers, it might forget that Harry was in Gryffindor. Or maybe this information was already inside the model, but just not upweighted enough that it produced the outputs, could be either. So I'm not saying that like all the Harry Gryffindor association is at this particular layer inside the model, but this is where it's the most prominent, that it like caused a visible change.
Seems like Ravenclaw's the favorite though.
I think that's because it's doing some sort of like induction head kind of thing. Like Ravenclaw is like the first token, so it just wants to copy that. And that is pretty common. Like if I just have the model output something with this prompt and sentence complete, it will like keep doing Ravenclaw, Hufflepuff, like again and again. It's yeah, it's one of the older Vithya models. I'm not fairly certain on its capabilities anymore. But okay, so this is just an example of like what can we do where we free people from having to implement everything, but just have to focus on like what are the interesting things that they care about. So that's why we are building this platform called Lumiscope. If you are doing any sort of mech-interp research, we would like to talk to you because we can develop other mech-interp methods in the same way. So imagine if all you have to do to implement a method was to look at the paper and the same exact figure was in your Jupyter notebook and you just play around with it. So if you want, you can sign up. We're doing a short survey. This is like a 1-minute form that just asks you if you're doing McInterp research and what kind of research. So feel free to sign up, but yeah, if you want me to make your work better and easier, then this will help. But people are excited about this because this means that a lot of people don't really need to implement a method anymore, but can focus on different things. And that's what McInterp research is about right now. It's about like finding these aha moments and insights, and the faster you get to that, the easier it is. All right, I don't know how much time I have.
About 4 minutes.
Okay, that's good because I still have a third of my presentation that I haven't presented. But all of this is about stuff that you can do when you kind of know what you're looking for. Like even in the second case, you didn't need labels, but you had a task. You wanted to like evaluate bias, you wanted to find associations, you wanted to find where the entities were located, etc. But what if you don't know what it is that you're looking for? What is a feature? What are the things inside the model that you want to figure out? What is the model doing? That is a very broad question, and people have been working on this. They're trying to find what the true features are for a model. And that leads me to the last part of my work, which I will not present, but I will just mention that if there are no contrastive labels, if we don't know what exactly is the task that a model is doing, how do we figure out what the features are, what these linear directions are in an unsupervised way? And that leads me to sparse autoencoders.
So can I say something?
Yes.
We do have 1 to 1:30 for discussion, and we've been discussing, so I would say that it's okay to talk more if people need to leave, because, you know, you have something else that one, that's fine too, but we did discuss a lot of things, and so I think it would be great to go through the rest of the presentation. Okay, but feel free to leave if you have to leave.
Okay, I will just go to the end for now.
Okay, okay.
If people leave in like a minute, after that, I will go back to where I left. Okay, so that leads me to what people have been really excited about in interpretability. Sparse autoencoders, where do I start? People have thought about this way long before. Sparse coding existed long before OpenAI and Anthropic decided to train their LLMs with sparse autoencoders, but they became popular last year. So I'll just give you a brief summary of what two of these models are. There are so many now. A sparse autoencoder is just an autoencoder that goes from the space of LLM activations to an even higher dimensional space where supposedly things are pure and sparse, so that one neuron inside this very large hyperspace just corresponds to one concept or one true feature. Now, the way the Anthropic people decided to do it was by inducing sparsity using L1 norm. That was a good start, but there was an obvious issue with this way of training your SAEs. If you look at the loss, it's not just trying to reconstruct the data anymore, it's trying to reconstruct the data and balance out the sparsity, which means that it would trade off some amount of reconstruction so that it can produce a sparser representation. And that is not what people like, because all you want to do is reconstruct your data well and find the sparse features encoded in it. But this started this whole chain of improvement, model variation, and different techniques of training the models that people are still working on right now. So another example is a TalkK SAE. This was done by OpenAI. All you do is remove the regularization sparsity. You have this extra term that sort of balances out how many neurons are dead inside the model, but you're not trying to balance out the sparsity anymore. You're controlling the sparsity by explicitly selecting how many neurons are active at any time. So TalkK function is just saying, if I choose K to be 2 at any point inside this like hyper dimensional autoencoder, only 2 neurons can be active to produce an output. So it means only 2 features can be active. Now, the obvious problem here is that the K is something that sort of either makes the model work or not, because if I choose the wrong K, who knows what will happen. Now there are like many other variations. DeepMind came up with gated SAEs, jump railway SAEs. They're just names, but they're different architectural choices and training schemes that sort of improve the previous iteration of the model slightly better. But I am going about it a different route. Let's say I know what the true features are. My data is not language anymore, but it's some synthetic data where I know what the true features are. I can construct the data set that I can train my SAE on. And if it works well, then I know that it could potentially work well on real data. If it doesn't work well, then I know for sure it won't work well on real data. Well, I guess I'll just skip this checkpoint. But this is a subset of synthetic data sets that I've constructed. It's just 3. But imagine if I had a 1D manifold, which just means literally my data is 2D circle that's noisy. I have 5 co-independent features, which just means 5 spokes in 5 directions. And I have bunched spokes where like 3 spokes are closer together. It's like very simple. All of this is 2D, but imagine this sort of happening in real data, because I see this happening in real data. This is some data that I produced from, again, like Gemma 2B, where I see spokes. These are all like widely different data modalities. One of them is like French, other is JavaScript code, third is like just emojis. So if they're like widely different, then you might see something that's similar to synthetic data sets. This is even more complicated, but this came from Max Tegmark's group. This is calendar features that go around the circle, but also have certain radius. And yeah, so like, even though these are like 2D or 3D features that I have shown, they sort of also exist in real data. So they're not too far-fetched, and starting this way isn't wrong. But yeah, so if I have autoencoder that goes from 2 dimensions to n, where n is larger than 2, for all of these examples, what happens? Well, we see why models work and why models don't work in certain scenarios. I'll very briefly say what happens in the circle first. So if you think about the linearity of these models and everything, the SAEs are supposed to find linear features, because that's the hypothesis, that everything is linear, everything to a certain extent is linear. So all they can find is linear features. Linear features for a circle are 4 orthogonal directions, because there's a ReLU. So you need 4 instead of 2. SAEs can find that with the right hyperparameters. But if you either go too far and choose the wrong set of hyperparameters, you would trade off some level of reconstruction loss to make it slightly more sparse. Maybe you don't really need that level of sparsity, but in a real model, you don't know that. You don't know what's the right level of hyperparameter to use. You don't know how many expansion dimensions to use. If you play around with it and choose the wrong set, you might get to a state where you reconstruct the data, but don't really find the directions that you use to encode the data. Now, this is not even the problem. The problem is, this is a 1D manifold, and technically I would be better off representing it with r and theta instead of the perpendicular directions, but there's no inductive bias for the model to recover that. So in this real data example that I had shown before of like the calendar features, what the authors see is that there is theta, the direction of semantic meaning, and not xy, so to say. If you go around the theta direction, you go from Monday to Tuesday, Tuesday to Wednesday. So if the model is supposed to find linear directions, it would find a direction that's like parallel to this, parallel to that, or maybe somewhere in between Monday and Tuesday. That's not the most semantic direction that, if your goal was interpretability, you would want to find. So what this means is some inductive bias inside the model would give you the right set of features. Now, what happens if you choose a neuron to be active in a way that maybe represents your data better? Because let's say I do know that this is a 1D manifold. I choose my K to be 1, so only one neuron is active at a time. What this does is that if I naively choose very high expansion dimensions, it would sort of find a summary of the actual manifold. And if I keep on going, it would not obviously find the right manifold, but it would be closer to finding the manifold and the features than this. But still, it's not the semantically meaningful direction that is being recovered. For that, that's something that I haven't shown here, but you could do that if you use a variational autoencoder with some like non-Gaussian prior. And if you do that, then you might recover spherical features. You need some inductive bias for the model to recover that. In this other example, sure, like you might be reconstructing the data well, but you may or may not find the right features, but there at certain level of sparsity, there's a sort of a phase transition and you find the right features. But obviously you're missing off on the actual magnitudes. Now, again, like I know that there is only one feature active at a time, so I can choose K equals 1, expand to 5 dimensions, and I can perfectly reconstruct the data, but I don't know that. And if I choose just 3 dimension, I learn some summary of the data that is not the right level of abstraction for that data. And this is also something that people at Anthropic see. What they call feature splitting is that if you train a SAE, if you train a larger SAE, there are splittings in the features that the smaller SAE found. And so you could keep on going until you find purer features, but you don't know how many there are. So right now, that's one of the issues. So reconstructions show the current issues with SAEs. There is feature splitting and shrinkage, which could be resolved with architectural choices. But if the model size is not large enough, or if you don't choose the hyperparameters well, the model might have to cut costs to figure out the features that it can represent at that level of hyperparameter constraints. Now, this is a more philosophical question. What even is language? Like, does language have infinite features that are being represented by these models finitely? Or like there are just finite number of features that the models can represent? And well, that depends on how you think about it. If the model can only represent X number of features to a certain degree and Y number of features with superposition, and that keeps on decaying as they become sparser and sparser, it means that you may or may not be able to recover all the features that the model learned, but who knows? People are working on making it better. That's sort of where I will end for now. But yeah, that's about it. This is my cat.
All right. Well, thanks, Shivam. Interesting stuff. I see some people are still around. If there are any final questions or comments. Otherwise, Shivam comes here regularly to the CFA.
Yes, I do.
On Fridays, maybe, is that when you're coming most? So, do you have a question? Sorry. No, okay. So anyway, we'll meet again in a week, and thank you very much for being a speaker. Thank you.
Thank you.